whenever you have them. There are no stupid questions, and simple questions like what is the abbreviation of VA or whatsoever. It's very important to know it, because if you cannot even fill in those numbers into a formula, you can't even get the exercise right. So today we will be doing chapter 11, exercises C, D, and J, which will all be acid-base titration exercises. I'm assuming all of you have access to these exercises. If not, just type in the chat. But I made I drew up schematically the first exercise, which is exercise C, 11C. And what they ask of us is to calculate the pH at different points of the titration. So they asked when the volume added is 0, 10, 20, 25, 30, 40, 49, etc. in volumes of titrant that we add to the system. We will not be handling all of these volumes that we add, because we simply do not have the time for that. We only have 2 hours. So some of these volumes are equal to each other, or they are at least calculated in the same way. So we will skip the some of them, and we will be handling the most important ones. And you can apply the same formula for different volumes as well. So as you can see here, I schematically drew kind of the question that is asked. So we have a titration with cocaine in our flask, and cocaine is a weak base, so it's able to accept a proton from water or from an acid. And we are going to titrate with nitric acid, which is a strong acid. So it basically dissolves into NO3 minus and just the protons. And there are a few steps to take to solve these exercises. And the first one is to write down the reaction of the titration. And you do not need to know the full structure of cocaine. You can just write down coca or cocaine, whatever you want, and its protonated form, right? Then you want to calculate the equivalence point of the volume that we add. I'm assuming you can all do this. It's also very important for the experiments on the practical. But if you have any difficulties, just let me know. We can discuss it nonetheless. Then the third tip is to figure out if your volume added to the system is before the titration happened, in between the start of the titration and before the equivalence point, like I wrote down here, whether it's the exact same amount as the equivalence point, or it's an excess amount, so it's after the equivalence point. And it's very important to realize that, because then you can clearly think about all of the molecules that are present at that part of the titration, right? So the question that is asked is to calculate for us what the pH is at different times of the titration. And I will let you work on the exercise for 5 to 10 minutes. But from my experience, some of you can do the exercise, but most of you will just watch me do the exercise for you. And I understand that completely as well. Yeah, so I suggest you get started with the reaction and the equilibrium volume. So when all of the cocaine has been neutralized. So there are some information points we get in the question. So the amount of cocaine we have is 100 milliliters with 0.1 molars of cocaine. Cocaine is a base, so it is able to accept a proton from water or an acid. And we're going to titrate with 0.2 molars of nitric acid. Yes, so it's important to realize that we start with a base and we are going to titrate with an acid. So we expect of the pH to be high in the beginning and to decrease while we are titrating and adding more acid to the system. So if there are no further questions, I will pull for it because none of you responded to my question about the group size. All right, can someone let me know what the equivalence volume is that you calculated in the chat, perhaps? $50 milliliters, right? So I performed the calculation already. So first, what we have to figure out is what the stoichiometry is between the cocaine and the nitric acid. So cocaine is able to accept 1 proton, and nitric acid is able to donate 1 proton. So the stoichiometry is 1-to-1, but the concentrations of both solutions differ. So there's an easy formula for us to calculate what the equilibrium volume should be. So it's basically the volume of the cocaine multiplied by its concentration divided by the concentration of the titrant, which gives us 50 milliliters. So I hope everyone could figure that out. And that gets us to the first part of the question, which is to calculate the pH of the point of the titration where we added no titrant to the solution. So it's before the titration has even started. I will let you work on how to solve this. I wrote down the reaction already for you, and the equilibrium constant as well. You will be needing this for the calculation. So guys, please let me know if I'm going too fast or too slow. Yesterday I gave the exact same tutorial and we had some time trouble. So today I'm trying to move faster a little bit. But if I'm going too fast, well, then we have to slow down, obviously. So did anyone already calculate the pH at 0 volume added? So the VA is an abbreviation for volume added. And the pH of the solution is only the cocaine that it's responsible for. So cocaine is a weak base, and the base constant of cocaine says something about how much of the cocaine dissolved into water will accept a proton from the water, which is obviously a very small amount, but nonetheless it is an amount. And with the equilibrium constant, you can find X, right? So I'm not getting a lot of reactions from you guys, so I'm going to pull if I'm going too fast. Because it's for me also important because if you do not give me any feedback or whatsoever, I do not know what you guys know or not know. I'm going too fast, okay. So Kai and Guess and Mout, maybe you can try to tell me which part you do not understand yet. Right, that's no problem. That's no problem. So you mean with calculating the volume of equilibrium, or the pH at the first part? Because if it's the pH calculation, I totally get it. Because you have to use the quadratic equation, right? Or in Dutch, the ABC formula. Yeah, sure. Okay. So today we will be skipping the ABC formula or the quadratic equation, however you want to call it, most of the times I will be performing it once, but after that I expect you to handle it yourselves, because it takes a lot of time to write everything down. And yeah, so I can just give you the answer of the pH, and maybe you can get calculate it in your own time. But it's fine. The most important part of these calculations is that you understand what you're doing. It's not about the final answer, right? So if your final answer is somewhere about 10 in SPH, then you know you are right. But the most important part is to know when you've add 0 milliliters of volume to the system, the pH is only adjusted because of the cocaine and not of the nitric acid. And whenever we are going to add something to our system, then it becomes a different kind of story. But I will let you work on the calculation for the first pH part. And if you have figured it out, we will proceed on to the next volumes. And then I won't expect you to calculate every single pH, because then we do not have enough time for today. Does everyone understand this part, right? So the x squared divided by the formal concentration minus x. So what's the formal concentration? It's basically what we think that the concentration of cocaine is, but it actually isn't, because some of the cocaine has reacted to the protonated form. So this is basically 0.1, right? And the x remains the x. We want to find x. Okay, so I'm going to show you the calculation. So this is the calculation, right? So x squared plus 2.6 times 10 to the power minus 6 times x minus the same times the formal concentration. Formal concentration is 0.1 molars, because that's the concentration of cocaine we assume that is present in the system. And x is exactly equal to the hydroxide concentration, right? Because if we skip to the previous slide, we see that x is here, right? So if we find x, we find the hydroxide concentration, and the hydroxide concentration is directly relatable to the pH or the POH, whatever you want to prefer. Right, so x is the hydroxide concentration, which is equal to 5.09 times 10 to the power of minus 4. I'm going to pull once if you guys understand how I got there by filling in the quadratic equation. And if you agree with me, then I will skip it for the upcoming exercises. So I'm getting, so Elina, Hidde, Janouk, maybe you can respond to the poll. All right. I'm assuming Hidde knows as well then. So the hydroxide concentration before the titration has even happened in the solution is this number, right? And with the hydroxide concentration, we can find the POH, because it's the minus log value of the hydroxide concentration. And we find that the POH is 3.29 and the pH is basically 14 minus the pOH. So it's 14 minus 3.29 is 10.71. So the pH before the titration has even happened is 10.71. And do you expect the pH to increase or decrease while we add more acid to our system? You can type in the chat. Decrease, right. So our next answer to, let me quickly see, volume 10 milliliters added should be lower than the answer we find here. If it's higher, then we did something wrong, right? So going to calculate what the pH is when we add 10 milliliters to our system, and the pH should be lower than 10.71. If this is the case, then we can assume we made our calculation right. So here I kind of drew up what the pH is and what it could be at the end of the titration. Right. So now you can also kind of draw the titration curve if you would like to. All right. So now we will be performing the 10 milliliters. And as you can see, we have to figure out where we are in our titration. Can someone kind of explain to me in which point we are? So in between the volume started and equilibrium, is it an excess? Is it the exact same amount as the equilibrium? Or, yeah, well, I'm not even gonna say that it's before the titration, because that just don't make sense. Let's see. So before equilibrium, after V0, and before equilibrium. Yes, exactly. It's very important to realize this, because if you can realize this, then you don't even have to think about the rest of the exercise. So there are just simple formulas which you can use when you know at which point of the titration you are. I'm quickly going to skip to the summary page of our tutorial for today. So this is kind of the first one that we just performed, right? So the added volume is equal to 0 because the titration has not even started. And we can find the pH by using the equilibrium constant with the quadratic equation, like we just did, right? So now we say our added volume is in between the volume when we start and the first equilibrium point. So in this case of this titration, we only have one equilibrium point, but we will also be discussing the diprotic acids. So we are here right now. So we have to use this formula right here. And I will kind of explain to you how you get to this formula. So I'm sure you all heard of the Henderson-Hasselbalch equation, right? Which is basically this. So the pH at volume added 10 milliliters is in between, is before the equivalence point, right? We just stated that. And the Henderson-Hasselbalch equation kind of calculates the pH when we take the pKa into account, which is directly related to the acid constant of cocaine, and also the log value of the unreacted fraction divided by the reacted fraction. And there are two formulas which you can use to calculate the unreacted fraction and the reacted fraction, which are listed here. And it looks like they are very large formulas and takes a lot of time to fill in. But actually, you can rewrite this formula into a very short way. And that's actually this. So the pH is equal to the pKa plus the log value of the equivalence point minus the volume that we add divided by the volume that we add. And that is because we can just fill in this part of the formula, the unreacted part, into the denominator, and we can fill in the reacted part into the denominator. And a lot of numbers will get kind of evened out, right? And the only thing that remains is this formula. So I will give you a heads up about this formula. It's something you have to be able to derive yourself on the exam. So it will not be listed on the formula paper. So you better memorize it yourselves because it's very important. You will always need it when you have to calculate the pH in between the volume started and the volume of equilibrium, right? So this formula is very important. You can always use it. If you do not prefer it and you prefer these two, you can always use these two, but this is just a lot faster, right? So I will let you think about this exercise, and I will let you work out the answer. There is one important side note, and that is that in the Henderson-Hasselbalch equation, the pKa is listed, and cocaine is a base, as you might know. So we first have to kind of use the base constant to calculate the acid constant, and with the acid constant we can calculate the pKa, right? Because it's basically the minus log value of the acid constant. So I will let you guys work on that for now. Can this formula also be applied when the reaction is with a polyprotic acid or base? Yes, it can be. I will get to that later. So if there are any questions or hesitations or whatsoever, please ask them now. I can answer them, and well, there is time now. So. So if you got the answer to what the pH is when we add 10 milliliters, just post them in the chat, so I know you are ready with this exercise. So 9.02, around 9.0. Let's see. So I'm getting 9.01, but I'm assuming you got the pKa right. So do you guys all know how to calculate the Ka if you have the Kb? I'm not really sure what the previous assistant already instructed you. we can briefly discuss it. Yeah, well, let's see. So Lopke says I did Ka is K W divided by Kb, and then the minus log Ka to get, yes, exactly. That's the way you have to do it. So if everyone can look at the formula Lopke wrote down. So this is a calculation of the pH. So we got 8.41 as the pKa value. And how did we get there? We know the water constant is the product of the acid constant multiplied by the base constant. We have the base constant, right, which is given in the question. It's 2.6 times 10 to the power of minus 6. We already used it to calculate the first point of titration. And the water constant is always the same, so it's 1 times 10 to the power of minus 14, which gives us the acid constant. And maybe they even give to you on the exam, but you should be able to calculate it yourselves. So it's listed here, the 3.85 times 10 to the power of minus 9. The minus log value of this number is 8.41. So from now on, we can let this 8.41 sit there for every calculation we make when the volume that we add is in between the equivalence point and the volume that we start with. Right? So in between 0 and 25. So I mean 50, sorry. So all volumes that we add in between 0 and 50, we can use this formula to calculate what the pH is. So this makes it no longer interesting for us to calculate the pH when we add 20 milliliters, because the calculation will be exactly the same, except we change the volume added. Right? So for 10 milliliters, we can just write down pH is 8.41 plus log value of 50 minus 10 divided by 50 is equal to 9.01. So I'm not really sure how you got to 9.02. Who was it? Yes. But I think you made some rounding error. Right? So this is the pH. So all of the volumes that we add for 20, 25, 30, 40, 49, 49.9 are exactly the same for this formula. I can write them down if you want to, and if you want to check whether your answer is correct, and I can give you the pH. But for this tutorial, it's not very interesting for us to calculate every single volume when it's the exact same calculation. It becomes more interesting when we get to a different point of the titration. So there's a question. Let me just. I didn't round of pKa. Oh, right. I think on the exam there is some kind of error you can deviate from the eventual answer. So if you deviate like to part of 100, then it's fine. I'm not really sure, but I'm guessing they won't correct you for it. So I'm going to pull, if you are ready to discuss the part when the volume added is exactly equal to the equilibrium point. So when the volume added is 50, because we already stated that the volume of equilibrium is 50. So If not, and if there are any difficulties, just let me know, and we can discuss that part again. And if you have a question and you do not really know how to ask it in English or whatsoever, you can also ask it in Dutch, and I will translate it for you to all of you. It's also fine for me. Okay, so if everyone could respond to the poll. Eva, Janouk, Kai, Marjolein. Hit it. All right, Kai. Misclick, I assume. Okay, so I think Hit is just offline because he has not responded to any poll yet. So we will just proceed then. Yes? All right. So can someone tell me what kind of molecules are present in the solution when we added exactly 50 milliliters? Can someone type it in the chat? Because all of the regular, so the neutral form of coca has been reacted. All of the nitric acid has been reacted. So what is there? And how can we use these molecules to calculate the pH? Right, so all of the, let's just skip to this part. So when we add 50 milliliters, we are exactly at this point of the equilibrium. And I'm going to explain to you why you no longer can use the Henderson-Hasselbalch equation to calculate the pH. Because if we fill it in like we normally would, then we get the 8.41 plus the log value of 50 minus 50 divided by 50. So what we would get is 0 divided by 50, which is unsolvable, right? So there must be another way to calculate the pH then, right? And there is, in fact. So all of the cocaine has reacted to its protonated form, but that doesn't mean a part of this cocaine, protonated cocaine, will react with water back to its neutral form. And this reaction is based on the acid constant, right? So it's this protonated form of cocaine basically behaves like an acid, a very weak one, but an acid, right? So it can donate its proton back to water and form the neutral form of coca, and also produce some acid to the solution. And the way to calculate it, to calculate the pH, is basically exactly the same as the volume 0, right? So I've listed here all of the volume formulas. Maybe you can take a screenshot or whatsoever. So it's not this one. It's basically this one. So we discussed this one, we discussed this one, and now we get to this one. And the reason for all of these formulas being here is because with diprotic acids, you obviously have 2 equivalence points. So it gets a little bit more complicated. But the volume added is equal to the equivalence point, and we use the equilibrium constant with the quadratic equation again. But now we do not use the base constant, but we use the acid constant, right? So what was the acid constant again? We calculated it here. So it was 3.85 times 10 to the power of minus 9. And the formal concentration has been decreased. And the reason for this is because we no longer have 0.1 molars of cocaine, because we added 50 milliliters of nitric acid to the solution, which has all been reacted to water with the cocaine. But nonetheless, this means that the solution has been diluted, right? So this is just a formula to calculate the new formal concentration with the formal concentration that we had, with the starting volume and the volume that we add. So basically there has been a decrease of 33% of the concentration. And the new formal concentration is 0.0667 molars of protonated cocaine. So it's less. And with the equilibrium constant, we can use the acid constant to find X. And in this case, X is the same as the proton concentration. Proton concentration is related to the pH. And the minus log value of the proton concentration is the pH. So when we add 50 milliliters to our system, so I'm going to write it down here, our new pH becomes 4.80. I will let this white screen be here for a few minutes, and I will ask if there are any questions about this part. Because guys, I'm not getting a lot of feedback from you and input, so I'm not really sure whether I'm going too fast or too slow, even though I included a poll for it. So Kai, the new formal concentration, the first formal concentration we used to calculate the pH before the titration has even started, and now we have added 50 milliliters of kind of water. We can say it's water, right? Because everything has been neutralized to our system. So our system no longer has 100 milliliters. It has 100 plus 50 milliliters. So when you can kind of compare it to like lemonade, right? Syrup. When you add some water to it, it gets diluted. So the concentration of the sugar molecules decreases. And this is the exact same principle. We add 50 milliliters to 100 milliliters, and that's why our formal concentration of cocaine decreases. Does this answer your question? If not, just say so. I can. It does, but it's also diluted in the previous one, right? No, it's not, right? So let's look at the first one. So the first one, was to calculate the pH when we added 0 milliliters of nitric acid. So the system still has 100 milliliters of cocaine. So to calculate this point, we use the formal concentration of 0.1. But now we have to correct for the dilution factor for it. Let's see. The one with the 49 milliliters I meant. I don't think we discussed the 49, but I think you meant the 10 milliliters, right? But for that part, we can simply use the Henderson-Hasselbalch equation, which is way more easy to calculate the pH. It does not even take the dilution factor into account, or, well, it does. If you look here, you see? Because the dilution factor divided by the dilution factor gets kind of evened out. So this is the dilution factor we also correct for here at the 49 milliliters, like you see, but divided by the exact same dilution factor, it does not influence it. So we do correct for it, in fact, but you will not see it in the eventual formula. Right, so I can highlight it for you. All right, nice. So I know it's a lot to take in, and it feels like it makes sense when I show it to you, but if you have to do the exercise yourself, you will get stuck somewhere. And this happened to me as well when I followed the course, so it's just natural. When you perform the exercises multiple times, it will become more easy. All right. So did I make a poll? So there's one no. Oh, that's from Kai. Yanuk, are you ready to proceed? Okay. Then we will get to the excess amount point. So after this first equilibrium volume has been added, all of the nitric acid that we add to our system does not react with cocaine because there is no cocaine, right? So all of the cocaine has been reacted to protonated cocaine. So when we add more acid to our system, it will not donate its proton to cocaine. It simply will become dissolved in the system and influence the pH on its own. There's a question. But after the equivalence point, the dilution factor is V minus V added. Is it just a rule to use the one formula before equivalence point and one after the equivalence point? I'm not really sure, Lopke, what you mean. So after the equivalence point, the dilution factor is. Yes, it's kind of the rule for the formula. I will show you. So after the equivalence point, this is basically what we're dealing with. So before the equivalence point, it was kind of messy, and all these different molecules are present, and you can calculate the pH by determining the unreacted fraction and the reactive fraction. And after the equivalence point, all of the molecules that influence the pH are no longer present, or, well, they are, but we do not use it to calculate the pH. We simply use the excess amount of protons that we add to the system to calculate the pH. So in my opinion, this is basically the most easy part. And this is the formula that we use. So it's basically volume added minus volume of equilibrium. So in this case, when we use, for example, 60, so 60 is larger than 50, 60 minus 50 divided by 100 minus 60 multiplied with the molarity of the titrant, which is 0.2 molars, right? Because the nitric acid. And this will calculate the I'm not sure. This should not be the OH min. It's for the next exercise. So this calculates the proton concentration. So you can repeat this formula for every single part after the equivalence point has been reached. But the formula stays the same. The volume added just will change. Right, so volume added is asked of us, let's see, 50.1, 60 milliliters. They both have the same calculation. I can perform one like I did here. So 0.1 molarity of the nitric acid times 60 minus 50 divided by 100 plus 60 gives us this proton concentration, which is directly relatable to the pH of 3.88. So for the volume added 50.1 milliliters, it's 3.88. Well, this does not make sense. Just a second. Should be the other way around. Oh, it does make sense. Never mind. But it's just the wrong numbers. So the example is this one. You can also repeat this formula for 6 milliliters, which will give you the 1.90 as pH answer. So what did we see? We started with 10 point something, right? Before titration happened. Let's see, 10.71. Then we went to 8.41. We skipped a lot of volumes that we add. Then we went at the exact equivalence point at 4.80. And after the equivalence point, we even decreased to 3.88 and eventually to 1.99. Right. So this is basically the most basic form of acid-base titrations. And the next exercise will be about a diprotic acid. So there will be one more formula actually, and we can repeat the formulas that we know now for other parts. But first, I'm going to pull if you all understand the first exercise. So questions about exercise 11C. Kai has a question. You can also unmute your microphone, by the way, if that makes if that's more convenient. Kai says, did I miscalculate or was the pH 2.88 instead of 3.88? Well, I kind of wrote down the wrong calculation, so it's 50.1. So I can perform it as well, but I don't think that's. Let's see. 50.1 minus 50 divided by 150.1 times 0.2. The minus log value of this one. Right. So I'm getting at 3.88. I'm sorry. You're right. 2.88. 2.88 is 51. Good of you to notice, Kai. So 50.1 is 3.88. And 51, because I think you calculated with 51, Kai. 51 milliliters is 2.88. Does this answer your question? Yes, all right. So, no questions about exercise 11C. Iggy, I'm not sure whether I pronounce it right. You're still unreacted? All right. Okay. So let's quickly go to the summary, right? To kind of summarize all of the formulas that we use. So the formulas that we use for this titration is the first one, like we discussed. So we use the equilibrium constant of the base one. The second one is the Henderson-Hasselbalch equation, which we kind of wrote in a shorter way. The third one was at the exact equivalence point, and we did not use the base constant, but we used the acid constant for this part. And the last one is actually this one. So it's the molarity of the titrant. We multiplied it with the dilution factor to get the proton concentration. And I marked with yellow the diprotic acid base formulas, but it's in fact this one and not this one. So that's kind of my mistake. Just a second. So these two formulas will be included when we will be performing the diprotic acid titrations. I'm sorry. Right. So for the next exercise, let's see what the exercise is. So it's basically the same exercise, but now we are dealing with malonic acid, so not a base, but an acid. And as you might figure out yourself, it's a diprotic acid. So malonic acid is able to donate 2 protons to the system. And we are going to titrate with sodium hydroxide, 0.1 molar. And we have to calculate the pH at certain points of volumes that we add. So 0, 8, 12.5, 19.3, 25, 37.5, 50, and 56.3. And I will let you guys figure out which volumes we will discuss by first letting you calculate the equilibrium point, the first one and the second one. And if you found them, you can type them in the chat. And by the way, guys, I'm sure your previous instructor also mentioned it to you and also in the lectures as well. So we are dealing with a diprotic acid, but it's important to first state whether the acid we are dealing with we have to treat as a monoprotic acid. And most of the time, well, actually all the time, you will have to be treating it as an monoprotic acid. And what that actually means is that here I wrote down the form, the malonic acid form, like we're dealing with, and it's able to donate a proton once, and it will get kind of the HM minus. And there's also the malonic acid 2 minus form. And what it means when we have to treat it as a monoprotic acid is that when we add a base to our system, some of the malonic acid will be reacted to its intermediate form, right? But because we have to treat it as a monoprotic acid, first, all of the molecules of the normal malonic acid will react to its intermediate form, and when this has happened, and only then will it will react to its fully deprotonated form. Okay, guys. So there's an easy way to check whether you can treat it as a monoprotic acid, and that is by dividing the first acid constant by the second acid constant. So there's a question. So Lopke already calculated the equilibrium points very well. I'm going to wait a few more minutes so everyone can calculate it, but you figured it out. So I think Sabet mentioned in the lectures that when you divide the first acid constant by the second acid constant, and it's more than 100 times larger, then you have to treat it as a monoprotic acid. And in our case, we are dealing with an acid constant of 1.42 times 10 to the power of -3 for the first Ka. So basically, this is the first Ka, and this is the second Ka, right? The first Ka is, I think, given in the given as a number in the exercise. I can write it down for you. The second one is, so you can already see it's about 1,000 times larger. And if we actually divide them by each other, we get as an answer somewhere around 700 or so, 750. So this is obviously a lot larger than 100. So treat as monoprotic. So one more time, what does it mean when you have to treat it as a monoprotic acid? It means that first, all of the malonic acid in its most neutral form will react to the intermediate state. And if everything has been reacted so that there is no malonic acid left, then when we titrate further, we will get the fully deprotonated form, right? So that's basically what it means to treat it as a monoprotic acid. So Lopke, you gave the equivalence points, and that's correct. If there are any questions about the calculation, just ask them now. I will write it down very shortly, not with the formula, just with the simple numbers. So we have 50 milliliters, right, of malonic acid, and the molarity of the malonic acid is 0.05 molar. So we multiply them and divide them by the molarity of the titrant, which gives us 25 milliliters for the first equivalence point. And the second equivalence point, how do you calculate it? Well, it's basically 2 times the first equivalence point. That's how easy it can be, right? So 50 milliliters. So Lopke, you were right. And how do we proceed now? How do we proceed with the first exercise? So the first exercise is to calculate the volume added 0. So can you type in the chat how to approach this question? Maybe you wrote down the formulas that I gave. So I will write down the equation. So volume 0 is before the titration has even started, so there is no hydroxide in the system present. So the malonic acid will just react naturally with water and donate one of its protons. And become as an intermediate state or amphiprotic, however you want to call it. So, any suggestions on how to solve the pH when we add 0 milliliters of sodium hydroxide? With X and Ka1. Do you agree with Lopke? Well, Lopke, no one's responding. Maybe I'm going too fast, I'm not sure. But yes, in fact, you are right with the Ka1. So it's very simple, actually. It's the same as the previous question. So this does not differ from the last exercise. So it's basically x, and the Ka1, which is given in the exercise, is equal to the x squared divided by the formal concentration minus x. And the first acid constant is equal to 1.42 times 10 to the power of minus 3. Right? So when we fill this into the quadratic equation, this equation, we find for x 7.75 times 10 to the power of minus 3 molars. And this is exactly the same as the proton concentration. So the minus log value of this number is equal to 2.11. So our pH is 2.11. Does everyone understand this? Yes, all right. So it's basically the same as the previous question. I find the previous question to be harder because for some kind of reason, bases are always the other way around, and people tend to mix those things up. And when we are dealing with an acid, the Henderson-Hasselbalch stays the same, the Ka stays the same, so should be easy, right? So did everyone get why I got from here to here? All right, thank you guys. So that's the first part of the titration, and that is an answer 2.11 as a pH. And does this make sense? Well, I think it does, because we dissolve an acid into 50 milliliters of water, I think, and well, we obviously expect the pH to be low, right? Because we dissolve an acid. So when we add the hydroxide to the system, so the sodium does not contribute or whatsoever. So when we add the hydroxide to the system, we expect the pH to increase from 2.11 onwards. We do not know what the endpoint of the titration will be, but we can figure that out. So the first point of the titration will be the volume added of 8 milliliters. Do you guys have a suggestion on how to figure out what the pH is on this part? H. Right. Henderson-Hasselbalch equation? Yes. So it's basically the form like we know it. So I'm not going to write down the whole part about the unreacted fraction and the reacted fraction. I think you figured it out that by now. So the pH is the pKa plus the log value of the volume of equilibrium minus the volume added divided by the volume added. So basically what this part is the unreacted fraction, right? So we can fill it in. Can someone type in the chat what the pKa is? Oh, never mind. It's the other way around, of course, because we're dealing with an acid. My bad. Oh. So when you're dealing with an acid, it's this way in the denominator. When you're dealing with a base, it's the other way around. So I'm used to writing down VT, which means volume toegevoegd in Dutch. It's the same as volume added. So, or you could say maybe it's VT as in volume titrant, but whatever. We're using volume added now. So can someone type the pKa of the first reaction? (2.52). How did you calculate this? It's the minus log value of the Ka1, right? So this value, the minus log value. Yes, same. I'm getting a 2.85 as well. 2.84, 2.85. So I think you messed something up in the calculator. I'm not really sure, but at least it's 2.85 plus the log value of the volume that we add. So in this case, it's 8 divided by the first equivalence point. It's 25 minus 8. So what's the pH? There's a question. Right. Okay. So what's the pH of this part of the titration? It's 2.52. Right, so we get 2 points in our titration, 2.11 and 2.52. So we get an increase of the pH. So we know our calculations presumably were right. Okay, so we can repeat this for every part of volume added in between 0 and the first equivalence point, right? So 12.5 and 19.3 we can skip. If you want to discuss them, we can do them, but we can skip them. And there's also one tip I can give you guys. So 12.5 milliliters is actually half of the first equivalence point, right? Because the first equivalence point is 25, 12.5 is half. And there's some kind of, you call it in Dutch, vuistregel. I'm not sure how you call it in English, but there's some kind of rule which says when you reach half of the equivalence point, rule of thumb, okay. when you reach half the first equivalence point, or the equivalence point for that matter, you can say that the pH is equal to the pKa. And the reason for this being is when you fill in the 12.5 into the equation, I will quickly do it for you guys. So added volume is 12.5 divided by 25 minus 12.5. You will be dividing 12.5 by 12.5, and the log value of 1 is 0. So basically what the product of the log value is 0, and the pH plus 0 is obviously the pKa. So that's how you can find or easily know if the half of the equivalence point has been reached, that the pH is equal to the pKa, right? This does not mean that you do not have to calculate it or whatsoever, but it's just something to remember. So we will not be performing the 12.5 and the 19.3. I can give you the quick answers. So 12.5 is obviously the same as the pKa, like we stated, so 2.85. And the 19.3 is just filling in another tiny formula, gives us a pH of 3.38. So it increases, and it increases. So it makes sense, right? So that brings us to probably the hardest part of this tutorial. And that's the point where we reach when the volume added is exactly the same as the first equivalence point. So this is only of importance when we are dealing with a diprotic acid. And the formula that we use for this part is this formula. So when we try to figure out what's all in this formula, we see the Ka1, the Ka2, the formal concentration, the water constant, and one more time the formal concentration. And the square root of this one will calculate the intermediate form. And the reason for this being is because we do not know in what kind of manner the intermediate form reacts back to the malonic acid or reacts to the fully deprotonated malonic acid form, right? So this formula, you will get it on the exam, by the way, this formula. It's only to calculate the pH when the titration has reached the exact point of first equivalence, where everything that is present in the solution is the amphiprotic one. So this one. And then we use this formula. I will give you 5 minutes to fill in this formula, or 10, whatever you prefer. In the meantime, I'm going to set up a poll if you think it's going too fast or too slow. So could everyone try to respond to the poll? Are we still listening, or are we distracted? I get if you are distracted, it's 5 o'clock. So Hidde, if you're not paying attention, I can remind you that the attendance at the tutorials is not mandatory. So if you do not want to come or whatsoever, it's also fine. Maud, are you there? All right. So someone says it's not going too fast, not going too slow. Ah, right. Okay, thank you. Yeah, so at this pace, we won't be able to discuss all of the exercises in 2 hours. But that's fine because the last exercise, exercise J, will most likely not be on your exam. And if you find the time, you can try to work it out yourselves with the solutions to do the exercises. Okay, so we fill in the new formula that I gave you with the intermediate state. And what's important to realize is that the formal concentration again has changed because we added 25 milliliters to our system. This means that the formal concentration of malonic acid that we had has been diluted, and this time it has been diluted 25%, right? So the formula states the formal concentration multiplied by the volume start divided by the total volume, so 50 plus 25, gives us the new formal concentration of 0.0333, and that brings us to the proton concentration we find. So that's kind of convenient about this formula. So it directly calculates the proton concentration, and that makes our life a little bit easier because it's directly relatable to the pH. So the proton concentration we find, if you fill in every single number in the formula, we know the Ka1, we know the Ka2, we know the formal concentration like we just calculated. We know the water constant, right? It's 1 times 10 to the power of minus 14. So here's the Ka1 again, and the formal concentration again. So if there are any questions about this formula or how to fill it in, then just say so. But I think it should be clear now. So our new pH becomes 4.28. So that's the pH when we add 25 milliliters, right? Volume added is 25 milliliters. So when we go back to, let's see, where were we? 2.11, 2.52, 2.85, 3.38, and then to 4.28. It makes sense, right? The pH increases. So Kai asks, let's see, what's Ka2? Do you not know the definition of Ka2, or you just don't know the number right now? The JR? What's the JR number? Oh, right. So I think the number is listed in the exercise, but I'm not sure. Oh, it's not. So you should be able to find it in Harris. But I can give it to you, of course. Let's see. Ka2 is 2.01 times 10 to the power of minus 6. I will write it down for you. So briefly repeat Ka1 and Ka2. 2.01 times 10 to the power of minus 6. 1.42. Right. So these are the numbers you need, and I assume that you know the water constant. It's always the same. That's why it's called a constant. Okay. So that's the pH of the second. The volume added is 25. So that brings us to the next volume that we add. That is, let's see, 37.5. So there's something about this 37.5, right? So does anyone know which formula to use? So where are we? we are basically in between the two equivalence points, right? Because the first one is 25, and the second one is 50, and 37.5 is exactly halfway. So what formula do we use for this part? And what's so different about the formula that we used when we were in the part where it was in between 0? So how is this different than this part? For example, we had 8, I think. So now we're discussing 37.5. So we can use the Henderson-Hasselbalch equation again, and it's almost exactly the same form. And we have to correct for some volumes that were lost because they are neutralized already. So the volume that we add to the system minus the first equilibrium, because that's the sodium hydroxide that has been neutralized already. So what we get is, well, I will write it down for you. So it looks like the formula has changed, but in fact, it corrects for the first equivalence point that has been reached already. So in this case, we can just write down 37.5 minus 25, and that makes sense, right? Because we have 12.5 milliliters added to the system because we correct for the first 25 that are not responsible for the second equivalence point that has been reached, because that was all before the first equivalence point, right? So it's 50 minus 25 minus 37.5 minus. So it basically gives us 12.5 divided by 25 minus 12.5. So what was so extraordinary about this part? What was so extraordinary is that the answer to this part is 1. So the log value of 1 is 0. Right? So it's the pK plus 0 is equal to the pH. So what's different now then? What pKa value do we use? Do we use the pKa value 1 or do we use the pKa value 2? Because we are dealing with this reaction, right? So the intermediate state will donate its last proton and become fully deprotonated. Yes, we use the pKa2. So the pKa2 is basically the minus log value of the Ka2, right? So it's 5.7D. So what's the pH then? The pH is then exactly the same to the pKa2 because the product of this log value is 1, log 1 is 0. Right? So when we add 37.5 milliliters to the system, the pH becomes 5.70. So it's still increasing. And this, this is logical, right? Because we add more base to the system, so the pH increases. So For all of the volumes in between 25 and 50, you can repeat this process and fill in numbers for this exact same formula. So it's basically the same as the first part, but now you use a different pKa. For this part, you use the pKa1, and for this part, you use the pKa2. I hope this makes sense, because for this part, we went from the malonic acid to the intermediate state, and for this part, we went from the intermediate state to the fully deprotonated form. I'm going to pull if this makes sense. All right. Yanuk, are you still here? All right. So that brings us to the almost the last one, and that's the volume 50. So I don't think we have to discuss it. If you have a suggestion on how to solve it. So when volume added is 50, how do we approach it? How do we calculate the pH? Maybe Lopke knows. So 50 is the exact equivalence point, the second one. So how did we calculate the pH before, when we reached the equivalence point? Quadratic equation X and Kb1. Right? Yes, exactly right. So for some of you, it's not very clear on what this means. So you have the normal malonic acid form. It reacts to the intermediate state, and then it reacts to the fully deprotonated form. This is the Ka1. This is the Ka2. So this obviously means that this must be the Kb1, and this the Kb2, right? Because the first proton it can accept is according to the first base constant, and the second proton it can accept is according to the second base constant. So they are in relation to each other. So how do we calculate the Kb1 of Lopke? Kw divided by the Ka2, right? Yes, exactly right. So Kw is equal to the product of Ka1 times Kb2, or the other way around. Kw is equal to the Ka2 times the Kb1. Do you have the Kb1 for me? So the base constant? should be 4.98 times 10 to the power of minus. Yeah, it's approximately that. Yeah. So let's say it's 4.98 times 10 to the power of minus 9. No, it should not be a problem. I don't think it should be a problem. So we use the 4.98 KB1. So it's basically this formula again, right? KB1 is equal to the x squared minus the formal concentration. So it's the new formal concentration. So the dilution factor has been corrected for this part, which is 4.98. And we get the formal concentration is 0.025 because we diluted it with 50 more milliliters. So we basically diluted it twice, right? So we started with 50 milliliters in our system. We added 50 more. So this means that our formal concentration has been diluted 2 times, right? I can write it down for you if it doesn't make any sense, but I hope it does now. So the new formal concentration is 0.025 of this part of the molecules, right? So for the whole titration, some of the malonic acid has been reacted at 25 milliliters. When we added 25 more, all of the malonic acid has reacted to its most deprotonated form, and the formal concentration has been decreased 2 times because we added the same amount of milliliters to our system. And that brings us to when we find x, because we use the quadratic equation again, we find for x 1.11 to multiply it by 10 to the power of minus 5 molars. And this, of course, we can use to calculate the pH, or first we calculate the POH, because we are dealing with an hydroxide ion that we get, right? Because the reaction is this. F minus X, X, X. So X is equal to the hydroxide concentration, and with the hydroxide concentration, we can calculate the POH, and we can also calculate the pH, right? Because 14 minus the POH is the pH. And we get as a final pH answer 9.05. So it has been shifted high. So pH is above 7 now. So it's a very basic, or not very, but it's a basic solution. All right, so that's the equivalence point 50. Then there is the last one we will be discussing for this exercise, and that's when we have volume added 56.3. And that should be larger than the second equivalence point. So what was the formula again that we used when we add an excess of proton or hydroxide ions to the solution? Maybe I can skip back to the formula sheet. So Lobke or Mout, do you know which formula to use for the excess amount of titrant added to a system when all of the molecules have reacted? The last one, the empty times the dilution factor. Yes. So can you work it out for me? Because I think you will learn the best when you do it yourselves. So it's basically the molarity of the titrant times the excess amount of hydroxide ions divided by the total volume of the solution. So if you have found the pH, type in the chat, and I will perform the calculation myself. In the meantime, I will write down the titration curve we followed. So we started somewhere around, what was it, 2.88 or something? So we started somewhere around 2.88. And we reached the equivalence point 1. And later the equivalence point 2 had a larger impact. And we ended somewhere around, let's say 10 or so. So this is 25 and this is 50. So I will write it down for you what the formula was. Maybe you gave it some thought. So the hydroxide concentration, and there's a question. 11.77, yes, exactly right. Good job, Lopke. The hydroxide concentration is equal to the molarity of the titrant, which was, I think, 0.1 molar. So this is the sodium hydroxide, of course, because that's the one that contributes to the new pH, because all of the malonic acid has been reacted, and the only thing we're adding to our system is the hydroxide concentrations, which are present in our burette. So the concentration of the titrant times the excess amount of hydroxide ions. So what's the excess amount? Well, that's of course the amount that we add minus the amount that has been reacted with the malonic acid. So 56.3 minus 50, and then we divide it by 50 plus the 56.3. So what's this? This is the volume of the solution, and this is the volume in excess, because we know that the first 50 milliliters has been reacted with malonic acid. So what do we get? We get 6.3 divided by 106.3 times 0.1 gives us 5.93 times 10 to the power minus 3. So that's the hydroxide concentration. The minus log value of this concentration is equal to 2.23, I think. And then the pH is POH, 14 minus POH gives us the pH of 11.77. So, Lopke, you were right. Great job. Okay, so that was exercise 11D. I can let you work on exercise 11J, but I think I won't be explaining more to you because I think it's a lot to take in. But I can answer questions whenever you have them about exercise 11J. But this is not really it's not really a question that is asked on the exam. You will most likely get a question like, all right, calculate the pH at a certain point of the titration, and then they give you a volume added is 11 or so. And then you have to calculate the pH. So then you have to figure out, all right, let me get my formula sheet. Then you have to figure out which formula to use and which molecules are present at that point of the titration. So when the titration has not started, just the acid or the base constant with the quadratic equation. That depends on whether you are titrating with an acid or a base. Before the equivalence point, you use the Henderson-Hasselbalch equation, short right-hand, so unreacted fraction and reacted fraction. First equivalence point has been reached. When there is a first equivalence point, then you use this formula, which you will get on the exam, to calculate the M-Diprotic state. So this only applies when you have a diprotic acid. And then it's basically the same. So in between the two equivalence points, you have the Henderson-Hasselbalch equation again, but you correct the volume that you added to the system, which had been reacted already. And then we have the moment when we reach the last equivalence point. So in case of a monoprotic acid, so when it can only donate one proton, this is the formula that you use. So it's basically the same as the first one, equilibrium constant with quadratic equation based on what molecule is present when it's an acid present or conjugated acid. You use the acid constant. When it's a base or conjugated base, you use the base constant. And when there's an excess amount asked, you use the molarity of the titrant and you multiply it with the dilution factor. So basically the excess amount divided by the volume present in your flask multiplied with the molarity. So I highlighted the formulas that are applicable when you use the diprotic acids, and the other ones are also used for just the regular acids. So there's a question. Katz asks, will we know what is and isn't on the formula sheet before the exam? I think there is some kind of example which shows a formula sheet. So yes, I think so, but I can ask for you. But I will tell you that the Henderson-Hasselbalch equation, short right, like we did with the volume of equilibrium minus the volume added divided by, you will not get it on the exam because you have to be able to derive it yourself. Right? So please do memorize that. So you can proceed with 11J. If you have any questions, ask me. I don't think there is enough time for you to do the exercise and for me to explain it before 5:30. So if you are feeling like you don't want to practice chemistry anymore, then feel free to leave. And if not, then I will be here for 8 more minutes.